All right. Hello, everybody. Welcome back to Comp 2452. I hope that you had a great weekend. Gosh, it's like snowing outside right now. I don't know about all of you, but like I keep seeing these positive temperatures in the forecast, but somehow spring seems infinitely far away. Like no matter how close we get, is just off in the distance. Yeah, I mean, I know it's going to happen, but I don't know. This is the time of the year where I start pining pretty badly for like getting out on my bike and riding on dry, smooth pavement, not ice and snow and stuff. Yeah, anyway, I hope you had a good weekend. I watched another Miyazaki movie over the weekend. We watched My Neighbor Totoro this time, which was really adorable. My daughter loved it. My son also loved it. I don't know that he'd admit to it. Like he's getting old enough now where he doesn't think stuff like this is cool, but Totoro, as soon as I saw this monster, it's just like, that's Snorlax. That is 100% Snorlax. And I don't know if that's intentional on the part of the Pokemon designers, but yeah, that's 100% Snorlax to me. Let's talk about our class. So what I want us to be able to do by the end of today's lecture is we're going to finish this part up. I want you to be able to describe and implement basic AI algorithms. And so last week we were talking about Markov chains. Today what I want to do is spend a little bit of time reviewing Markov chains. I want to spend some time thinking about Markov chains in the context of the task that I've given you for the last part of your projects. And then I also want to think about Markov chains in the form of random numbers. So I do want you to be able to distinguish between this idea of pseudo-random and truly random number generators and random number generation. This might be something you've seen before, question mark? Have you seen this in any other courses before? I see one person shaking their head, two people shaking their head. One person is saying maybe yes, but that's okay. So that might be in a stats course that you saw it. Stats courses, okay, yeah, stats courses. All right, so by the end of today's lecture, I want you to be able to distinguish between these two ideas, pseudo-random and truly random number generators. And I also want you to be able to use pseudo-random number generators for reproducibility. Part of this lecture will be like, you should use math.random to get random numbers. But what we're going to discover is that math.random, at least in JavaScript, doesn't let us use a thing called a seed, which is a way for us to basically say, this is how you should start generating random numbers. It doesn't let us do that. And so I want to be able to think about that, and I really want to be able to think about that. So define the term seed and then use that in the context of we're using these pseudo-random number generators so that we can always get the same sequence of random numbers coming out of this thing. So I want to spend a little bit of time thinking about that today. But first and foremost, I want to take a little bit of time to review these idea of Markov chains. So we opened last week with Markov chains on Thursday with this idea that Markov chains, if you really squint at them, they look a lot like what a state machine looks like. They have states, they have transitions between those states, but what they do is functionally different from each other. Markov chains, formally, they represent this statistical model that is going to be this thing that's called a process, like how we're moving from one state to another based on observations that we've made. Let's take some time to review Markov chains. I'll hold this up for about 10 seconds, and then I will switch over to my Mentimeter slides. One of the things I'm going to ask you to do as part of this quiz is to train a Markov chain. So if you've got some paper that you want to do that with, awesome. If you want to use Mermaid to do that, also awesome. If you just want to do it in your head, I am impressed if you can do it in your head, because I can't do this stuff in my head. It's hard for me to think about this in my head. Okay, I'm going to switch to Mentimeter. I'll hold here for about 5 more seconds. All right. Here is our first question about Markov chains. Okay, awesome, yeah. So Markov chain, main parts of it are going to be the states and the transition probability matrix. The edges and nodes, I think I'll give some spiritual credit to this. Yes, we were representing this as edges and nodes, but what those edges and nodes actually represent is what I'm trying to think about here. So the states themselves are the nodes, and the transition probability matrix is what really represents the edges between those nodes. The words alphabet and emission probability matrix, again, I'm going to give some spiritual credit to that. The words in the alphabet are absolutely part of a Markov chain and this whole idea of how we represent what these different states are. But in terms of the main parts, I'm going to say that the states themselves, so actually having what those states are, is what's best for a Markov chain. And I'm also going to draw a brief attention to this. This says emission probability matrix. This one at the end here also says emission probability matrix. I want to make a small aside here. The small aside that I'm going to make is outside the scope of this course, so you can shut your brain off for a second if you want to. A hidden Markov model. This is an extension. This doesn't show a picture. Oh, it does show a picture. Good. This shows a picture. A hidden Markov model is an extension of a Markov chain. We've got Markov chains. When we think about Markov chains, when we move into a state, we emit a symbol. And we know exactly what symbol we're going to emit because we just moved into that state. Hidden Markov models extend on Markov chains in that it's not just probability of moving between one state and another. It's also when you get to that state, there are probabilities that you emit a certain symbol. So it's not just that you go to this state and emit the symbol. This is an awful diagram. I don't know why I brought this up. This is a really bad way to represent this idea. But as we move to these states, we also have to make a decision about what symbol is going to be used for this. The aside here for me is that hidden Markov models are used on things like, and I think I mentioned this last class, doing things like predicting genes in DNA sequencing data. So like given DNA sequencing data, this is just a really long string of A, C, G, and T, billions of letters of this. You can use something like a hidden Markov model to decide what something should be labeled as. So whether it should be a gene or not a gene, the beginning of a gene, the middle of a gene, the end of a gene. You can use these kind of structures to be able to do that. That's our small aside, but for us, the main parts of a Markov chain here are going to be the states and the transition probability matrix. Here's our next question. Okay, good. I'm glad that we're really glomming onto this one. A Markov chain emits output. It does move from state to state, and we use random numbers to make decisions about which state to move to. But when we actually get to that state, the thing that it's doing is emitting output from that state. State machines consume inputs. State machines don't emit outputs. Markov chains don't consume input, but they do emit output. Deciding what to emit, again, this is that aside of, this is what a hidden Markov model is, so you don't necessarily know what is actually going to be printed or produced as output as part of a state. And then this part here, this is state machines. So state machines are consuming input to move from one state to another, but a Markov chain doesn't consume input at all. It's really just about emitting output. Okay, good. I suppose that's the right structure of this leaderboard. Magnus Carlsen is the chess player, right? Yeah, why is Magnus Carlsen coming to art? Yeah, okay. Okay, so the next couple questions that I've got for you are about training a Markov chain. And so I'm going to give you this training data. I'm going to give you 60 to 90 seconds to train the model. Again, I welcome you to use Mermaid if you want, if you don't have a piece of paper. If you can do it in your head, awesome. And I've got some questions for you about the trained model. So I'm going to put a little bit of time on my clock here. I'm also going to train a model on this, and then we will take a look at some questions about this. Okay, do we need 30 more seconds still? Okay. Okay. On your own time, I urge you to look up badger, 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 mushroom, mushroom. This is before many of you were born. Oh my God, this is terrible. This is before many of you were born, that this was a popular Flash animation. Flash is something that almost none of you probably know about. Flash is what was around before YouTube was popular, and it was like, have any of you heard of Homestar Runner before? 3 of you. Okay, awesome. That makes me feel slightly less old. Homestar Runner is something I welcome you to look up on your own after class. But Badger, 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 Mushroom was like this song, and it's very catchy. But please don't play it right now because I just don't want to hear it. Okay. Here is the first question that I have for you about the Markov model that you have just trained. Okay, good. I'm going to go here. That's real big. There. This is my Markov model that I trained with this data. This one here, that's mushroom. We left the mushroom state 3 total times in the training data that we had. And when we left the mushroom state, twice we stayed in the mushroom state. And then once we went to the ham state. So we left it 3 times. We stayed in that mushroom state 2 times. So 66% of the time, 2 out of 3 times, we stayed in the mushroom state. I am just barely hanging on to this, but it looks like Mars is going to catch up with me here pretty quickly. I'm going to ask you one more question about this Markov chain. I'm going to open this by telling you that I didn't tell you how to do this before. So like everybody's on the same page here. I haven't actually told you how to do this, and this isn't a question that I'm going to ask you on a test, to be very, very clear. This is not how we're using Markov chains in this course, but it's a valid question to ask about a Markov chain. If you continue to see Markov chains, these are the kinds of questions that could be, that you can use to use a Markov chain to answer. No, I do actually, this is something we do actually want to do. I'm really sorry. I have 2 more questions for you. I forgot that I put this one in. This is something I would want you to be able to do. Yes, forgive me. Please generate a pizza from the chain that you have here. Oh my gosh, I'm really sorry. I'm messing up my own order of slides. This is 100% something I would expect you to do as part of this course. The next question is not something I would expect you to do as part of this course. If you need random numbers, a good source of random numbers is random.org. And here, I will even generate a sequence of random numbers for you here. I'm going to generate random values from 1 to 100, and I'm going to generate a sequence of those. Here is a sequence of random numbers for you to use if you don't have a dice in your bag. I gotta make sure I say this again because I don't want to be held to this. You are 100% going to be asked to do something like this as part of your project. This is a core part of the project, is to generate output from Markov chains. Yeah. I'm going to give you like 5 more seconds to generate some output here. Oh. Good. I'm really glad that many of you didn't stop. You just kept going because I didn't really give you an ending condition. I didn't say when you should stop generating pizzas. I'm assuming that the rest of you that haven't answered yet are just still stuck in this loop of generating toppings for your pizzas. Open the pizza hotline. You need a stat study. What do you mean by that? What do you mean by that? It doesn't really matter. Mushroom, mushroom, mushroom. Okay, awesome. Yes, good. Okay, the next question I'm going to ask you is a valid question to ask to use a Markov chain with. The next question is not something that I would ask you to do in this course. The next question is not something I've told you how to do. But I'm going to ask you this question anyway. I want you to try answer it. You are very welcome to talk to your neighbors. I'm going to tell you what the question is at a high level to give you like 30 seconds to think about this idea. I'm going to give you a specific example that I want you to answer the question about. The question very broadly is, given a sequence of outputs, what's the likelihood that this model generated that sequence of outputs? That's the question that I'm going to ask you. On the next slide, I'm going to show you an example of what the sequence of outputs is. And the question that we're asking is, what's the likelihood that this model generated this thing? So I'll let you think about this for 30 seconds, and then I'm going to move to the next slide where I will actually show you that thing. Okay, all right, I'm going to show you the sequence and the possible options that you have here. I didn't give you enough time for this. Forgive me for that. Okay, I'm disappointed that nobody selected yuck. The question that I'm asking you to do here is I want you to kind of go through, I'm going to pop over here to my Markov chain. This question is really asking you to go through, like, given the sequence of outputs, what are the probabilities that you went from one state to the next? To figure out what the probability of this entire sequence of outputs is from this Markov chain, you multiply those transition probabilities together. So for us to go from pepperoni to mushroom to ham to pineapple, we're going to do pepperoni to mushroom is 1 over 1. This is 100%. Mushroom to mushroom is 66%. It's 2/3. Mushroom to ham is then going to be 33% or 1/3. So now we're multiplying 2/3 and 1/3 together. So that leaves us with 2/9. This is where our 22% comes from. And then the last transition we're making is from ham to pineapple, and this is 1 over 1. So we're multiplying that again by 1 over 1 to get our 22%. I'm not going to ask you to do this on a test. This is something that you could expect to see Markov chains and especially hidden Markov models being used for. So what's the likelihood that you actually got this sequence of outputs from a hidden Markov model? That's a much more powerful question to ask than this, because in a lot of cases you can say it definitely emitted the sequence. It definitely emitted the sequence because it has all the symbols that you have in this thing. With a hidden Markov model, you can't definitively say it definitely emitted the sequence or not without actually going through the Markov chain itself. Does anybody have any questions about that? Yeah.
Yeah, so just to clarify, like we never actually have kind of like a starting state in a Markov chain that has the probabilities that we, for example, begin with a pepperoni or a mushroom, in the, like as our first thing that we generate.
So with the first thing that we generate, there's going to just be, it was generated by this state, and that's the place where you're starting at. The first kind of probability that we encounter as part of this sequence is going to be the transition between pepperoni and mushroom. So that first thing, and you might have noticed when we were doing that start state at the beginning last time, it was always 100%. You go from this start state to this next thing. It's also possible for the start state to go to other things. The contrived data that we had didn't really work well for having multiple starting states, but Markov chains don't really have starting states in the same sense that a state machine has a starting state. We just have states that emit symbols. We can be in them at any point in time. Yeah. Any other questions? Yeah.
I want to clarify for my sake. For a question like this, even you said it wouldn't be on a test, but if we were asked a question.
This specific question will not be on any tests. Right. Yeah. Like, not in this course. It might be in a stats course, but not in this course.
Right. Just utilizing like the
yeah, so this is I don't actually know what you've seen in terms of stats, but the form that you would see for this is the probability of state xj given state xj minus 1. And then you multiply all that together because you have a sequence of states j and j minus 1 before that. It's not even j and j minus 1 because you can have things like mushroom here has two different states that it can transition to. There's no minus 1 in that sense. It's just going to be two symbols that are next to each other. Yeah. Yeah. Yeah, when we're working with Markov chains, we don't really we don't have an actual start state like we do in state machines. It's more like this is just the first symbol that we have in the sequence that we're working with. I'll talk about this in a minute, but with your projects, the first state that you would start from is the last thing that was added to the cart or the last thing that you bought as an item for upgrades or buildings in the domain that you've got. So for if we were doing this for like making pizzas, it would be whatever the last topping that you added to your pizza was. That would be the starting point for where you're going to go next in the Markov chain for generating outputs. Okay, good. Yeah, good. Excellent. All right. Thank you all for participating in this. Let's take a look at the phase 3 implementation stuff. So I posted this up onto the course webpage yesterday. What I'm looking for you to do for your phase 3 implementation is to implement this auto buy feature. That's really what I'm looking for you to do here. When you submit this, I'm expecting you to really just submit everything. So your entire project, all design documentation, all source code, this is what I'm looking for you to submit as part of your phase 3 implementation submission. I'm also looking for you to submit the training data. This is for ease of grading on the grader's part. They will have a copy of the training data, but it's going to be easier for them if they can just extract your work and then run your code on that, as opposed to having to download it and kind of manage files and stuff like that. I've provided you with some training data, and I'm going to actually open that up on my terminal. This is week 12, lecture 21. I want to actually go to project, phase 3 training. So I wrote a program here. This is a program in C. And the training data that I provided to you, when this eventually stops, looks like this. The data that I provided to you on the course webpage has 2 million rows in it. It's a pretty big data set. It's, I think, about 70 megabytes of training data. And the data is comma separated, and it's using my labels. My labels are A, B, C, D, E, F, G, H, I, J, H. Yeah, I think I stopped at H. I'm going up to H. There's 10 symbols in my training data. You're going to have to make a decision about what A is in your model. So like, what product does A map to? What upgrade does A map to? What building does A map to? How you decide to do that is entirely up to you. But what this training data is really showing is that there's a transition from A to F, and then there's a transition from F to E, and then there's a transition from E to F, and then F to J, and then J to D, and so on. How you decide to map, again, all of my labels up to your actual data, that's entirely up to you to decide. I'm not going to tell you because I don't know what most of you have for your models, but that's kind of a decision for you to make as part of this. But you have to have at least 10 things to be able to work with. Yeah.
If you have more than 10 products, then there are a few products that won't be included.
If you have more than 10 products, then there's going to be some products or some upgrades or some buildings that will not be part of this training data, because I don't have enough labels for that. Yeah. Minimally, you should have 10. If you have more than 10, then those won't be part of your Markov chain that you build up. I'm going to make a small reference to this. I have hidden an image in this training data. I'm not telling you any more than what's in this README. I'm not going to tell you anything more than what's in this README about that image, but there is an image hidden in this training data. That's the end of the conversation. I welcome you to tell me. If you don't tell me, you'll never find out, because I'm not going to tell you what it is, but there's an image hidden in this training data. The training data itself, like I said, is a giant CSV file. It's got 2 million rows in it. Every row is of a different length, and it's got all 10 of those different labels. I'm going to go back to the course webpage here. When you're building your model, when you're training your model, this should be something that happens offline. And what I mean by that is you loading this app up should not also include training the model. That will take too long. I'm giving you 70 megabytes of training data. My web browser shouldn't have to chew through 70 megabytes of training data when I go to your web application, because it will just take too long for that to actually happen. The training of your model should happen offline. And what I mean by that is you should write a program that's separate from the rest of your application that trains a model. It builds up a model structure and it prints out that model structure. So it makes its own CSV file, or you print out some kind of a JSON structure that represents the Markov chain that you've trained as a result of this. What you choose to use to implement this is entirely up to you. What language you choose to use to implement this is also entirely up to you. You don't have to use TypeScript to implement this training program. To generate the data, I wrote the program in C. The actual part of my C code that is about generating the model is about 30 lines of code long. It's not a huge thing. You can use whatever language you want to do this, but what I'm going to strongly suggest is that you might want to use TypeScript just because you're going to have common structures that are used for training the model and then using the model. There will be some consistent structures that you're going to want to use between those two things. But if you wanted to use Python, for example, to train the model, you're more than welcome to use Python to train the model. The expectation then is that when your app is actually starting up, it's only going to load the trained model. It's not going to load up this 70 megabyte file that has 2 million rows in it. It's just going to load up the thing that has been trained as a result of the output. Yeah.
Markov chain or really included in the database?
You can have it be, so the question is about hard coding the Markov chain. You can have it be a file that is sitting alongside your application. So like the grader will run the training program. You'll spit out either your own CSV file or a JSON file. And then when we load your app up, you can look for that file to exist. Yeah. In terms of the README that you're writing for this, I'd be looking for you to tell the grading staff how to interpret what your output is. I'm going to really strongly recommend that you use a CSV file to represent your model that's been trained. So like the transition matrices that I showed when we were looking at this in class, because it's kind of straightforward to model Markov chains this way. But what I want you to do is tell the grading staff how to interpret this data. So are you actually putting numerators in this, or are you just putting the probabilities of going from one state to another as floating point numbers? So 0 point whatever is 10%. I'm giving you the flexibility to choose what language you want to use, but the grading staff should be able to run your training program with one command. So if you're using Java, I would expect them to run a Maven command. If you're using Python, I'd expect them to use pip if you're using any kind of dependencies. If you're using TypeScript or JavaScript, I'd expect them to be able to use something like npm or npx to run your software. If you're using C, I'd expect you to have a makefile that builds the software that you're using for that. Once you have this trained model, then the way that I'm expecting this to work is that you'd load the trained model on startup of your application here. So in the same way that you're doing create tables as part of the startup process, I'd expect you then to like open up the trained model, model.csv, and read that so that you can build up the structure of the model that you have internally. Once you've got the model, then I'd expect you to have the actual feature parts of this. And so feature is going to be using that model to implement the auto buy feature. I'm telling you that the Markov chain itself, this is an implementation detail of your domain model. This isn't something that you really need to make changes to your class diagram for, because this is something that really should be private as part of your game or your cart or some other kind of model object that you have already. It's how it chooses to get the next n things from the database that you've got is kind of up to that class. And then the last thing that I've got here as a general requirement is that you have to have at least 10 things. So to your question, if you have more, no problem, but you got to have at least 10 things so that you have labels to line up to all the labels that I provided to you. In terms of the implementation for this and the assessment of this, I'm assessing two different parts. The first thing that I'm assessing about what you've done is I'm going to assess the training program. Again, this is offline. I'm looking for you to write a separate program to do this. And what I'm looking for in your training program is the apparent correctness of your output. So we want to see what you have as a trained model, and then we have an idea of what our trained model looks like. So we want to be able to see what that looks like and kind of compare it to what we've got. And then the programming standards. So the same kind of programming standards as you've seen up to this point. The actual implementation that we're looking for itself, I'm looking for you to actually have 10 items to be purchasable in your inventory system. I'm looking for you to put the Markov chain in your domain model. So it should be part of the domain models, part of your model view controller architecture. Does it actually work? And the programming standards. So as you kind of move up to this, between level 2 and level 3 for this, level 2 is, it really looks like you have something implemented, but it doesn't seem to work. And level 3 is, it seems to work when we turn on the auto buy feature. That's the main kind of criteria that we're looking for here in terms of the implementation of the code that you've got. I'm going to give you some time to ask some more questions about this on Thursdays, just so you have a little bit of time to think about it. But I also welcome some questions from you right now, if you have any questions about this stuff. Yeah.
I guess you provided some additional reading of resources about how we figure out just how to implement things, interpreting the CSV and turning it into the coded Markov chain in our program or something like that.
So, I mean, I am going to spend a tiny bit more time talking about some suggestions about how to implement it, but reading CSV files is something that you would have or should have done in Comp 1020. So I'm not going to provide you with stuff about that. Yeah.
Are we supposed put all the products in the cart after the auto buys? Do a checkout?
I guess so the question is about putting the auto buy items in the cart. Yeah, that's what I would do. Is if I give you $500 and say auto buy, then I'd expect that $500 worth of stuff will show up in my cart. Checking out would be a separate operation. Yeah.
It's like a suggestion button saying that you can generate stuff like this, like to add some auto buy stuff in your cart, and kind of implementation can be structured that way, but just a button that you click and then it generates stuff.
It should just generate the stuff.
So you don't have to click.
Well, a button, I would click a button and then it will generate the stuff as a result of me clicking the button, yes. For the clicker game, I'm expecting more like a toggle, like a checkbox that says auto buy is enabled. And when there's enough money, it will then buy the next thing in the Markov chain that you can. Just decide which one to go to and then buy that next thing. Yeah.
Now that we have 10 different items, where are we expected to have it for each item? So the player can also buy them.
I would expect there to be 10 items showing up on your page, yeah. We're not looking for that as part of this, but I'd expect that I'd be able to see all the items that I can buy that would show up in the Markov chain, yeah. Any other questions? Okay, all right. There is a picture, I promise. There is actually a picture hidden in the training data. The link is a little bit of a hint. The link is a hint. The link is a hint. That's the end of what I'm going to say about this. There's no actual bonus credit for this, for the record. This is more like, I'm going to be delighted if somebody figures it out. That's the bonus. You know that I'm delighted. That's the bonus. I welcome you to work together if you want to figure out what the picture actually is. But yeah.
Also, regarding the result of Markov chain, are we allowed to compare our results together?
Of course, sure. If you want to compare the trained data that you get, you're welcome to compare that, yes. Okay, so I have some suggestions for you about your implementation of this. I'm going to really strongly recommend that you use an adjacency matrix to represent your Markov chain rather than using nodes and edges. So like when I say this, I mean, don't build class node and don't build class like edge to connect these things together. Use an adjacency matrix for this. Adjacency matrix here is this idea. Forgive me for 1 second. Adjacency matrix is this idea. So build up a two-dimensional array. The two-dimensional array should represent, each column and row represents a state. The same states are on both sides of the matrix. And the values that you have at these coordinates are going to represent the likelihood of moving from one state to the next. So we talked about this really briefly in class, but the idea here is that we've got this visual kind of graphical representation of our Markov chain up at the top. You are welcome to build this structure again if you want to, but I would advise against it just in terms of the kind of natural exporting of something. It's going to be harder to export this as part of your training exercise than it will be to export something like this. But the model that we've got here with these two different matrices is that at position here, bread, peanut butter, what we're saying is this is the likelihood of moving from the bread to the peanut butter state. So in the model that we've got here, this is 3/5 of the time we went from the bread to the peanut butter state. And so in the actual transition matrix that we would have here as part of this, to go from the bread to the peanut butter state, we're kind of saying that 3/5 of the time we're going from the bread to the peanut butter state. So 60% of the time we're going to the state. You're very welcome to use a visual structure like this. If you want to build class node and you want to have edges between nodes to represent all these things, I don't want to stop you from doing that, but your life will be made easier if you use matrices to do this as opposed to those kind of graph structures for this. Are there any questions about this before I walk away from it?
So there's sort of like a starting state there in that diagram as compared to like the example that we had where we didn't have a sort of starting state. Okay.
Now we don't have a starting state. The purpose of the starting state was to kind of say, I want to put bread in there in the first place. If I don't put bread in there in the first place, then I don't have any states to start from. This allowed me to have, like, there's a transition from start, this imaginary start to bread. I could have also just said, we have a bread to peanut butter transition, so I'm going to add both of those states to my model. And we kind of did that as part of the instructions for doing that. The start state isn't necessary for us to have in this model. Yeah.
So like, can we just fix one start state for our implementation, or should we just take one random?
As you're going through each of these lines, I'm kind of expecting you to say, like, there's a transition from A to J. So I need to add A to my model and I need to add J to my model. And then I need to add that there's a transition that goes between the two of those. On the next line, there's a transition from C to H. And so I need to add a transition from C to H here. You can have a start state if you want, but you don't need to have a start state for that.
In terms of the implementation, like which item should we start with?
When you are implementing this, what I would expect for your implementation of this, your auto buy feature, I'm going to go back to, I'm going to go back to the choices here. For the point of sale system, the thing that I would expect you to use as the start for what you would then generate for the next state in your Markov chain is the last thing that was added to the cart. So you'll have, I've got this list of things that are currently in my cart. It's item length -1 that's going to be, that's the start state for the next thing that you would generate to be added to the cart. For the clicker game, that can be the last, I just clicked on the same one here. For the clicker game, the thing that you start from here can be the last thing that you bought as an upgrade or a building in your model.
So the cart should be like filled with at least one item in order to have this feature of auto buy. Only then it should be open.
You have to have at least one thing in your cart to start from. You have to have purchased at least one upgrade or building to start from, yeah. Otherwise, I mean, you could implement this as just choose a random thing and then add that to the cart and then start from there. But it makes more sense to implement this as we're starting from something. Yeah. Yeah. Okay, yeah.
Is it okay with me to just implement it as random, like start with the random thing instead of having this check mark if they have something with that bar?
You should implement it as starting from something. Yeah. The underlying mechanism I'm looking for is recommended items. That's really what I'm looking for, but that's not really achievable with what we've got. Yeah. Okay, so my first suggestion is use an adjacency matrix. I welcome you to build up this graph structure, but using an adjacency matrix is going to be more natural in terms of your training program can spit out a CSV file, and the code that you're actually writing for your application can read a CSV file, and then use that as state transitions to go from one state to another. The other thing I'm going to suggest that you do, I hand waved this a lot when we were talking about this in class, moving from one state to the next. I'm going to suggest that you calculate probabilities using sums and random numbers that are based on the denominator as the outgoing value from all the edges that you have for this. I'm going to show an example of what I mean for this. And so I'm going to pop back over here, and we're going to use this model that we built up before. What we were doing last time was I'm gonna say that we were starting in the bread state here. I rolled a dice. I said, if it's less than this, go here. If it's slightly more than this, go here. And if it's higher than this, go here. But that was kind of hand wavy about how you could structure this. From the bread state, we have two possible outcomes. I'm going to highlight these for you. The two possible outcomes that we have from the bread state are to go to the peanut butter state or to go to the ham state. Those are the two possible outcomes that we have from here. When I was hand waving this, I rolled my dice and said, if it's 60 or less, go to peanut butter. If it's higher than 60, go to the ham state. And that worked. That was functional for us to actually be able to accomplish that, but it's hard to encode that in actual code. The way that we can do this is we can generate a random number between 1 and the denominator of the outgoing edges from this state that we're in right now. All of the edges that I have coming out of a state should have the same denominator. And I think it was over here last time about that denominator matrix. We could collapse that down into one column because they're all going to be the same value. But every edge going out of a state should have the same denominator value. So to decide which one to go to, we're going to generate a random number between 1 and the denominator. And these are going to be inclusive. I'm going to use this notation just to make sure we're on the same page. If I show you this notation, do we know what I mean by that? Inclusive and exclusive. I'm getting lots of nods and thumbs up. Okay, great. So it's between 1 to the denominator inclusive. And then what we're going to do is in the same fixed order, so every time you're in a state and you're making this decision, you should always use the same fixed order. Iterate over your edges. And keep a running sum of the numerator. So I'm going to generate a random number between 1 and 5 here, inclusive. I've got 2 different numerators here, 3 and 2. If I generate a 4, I'm going to start with the peanut butter state first. I'm going to add 3 to my running sum. And what I'm going to say here is 4 is still higher than 3, so I'm going to move to the next state or the next edge here. I'm going to add that outgoing edge value to this, and now 5 is greater than 4, so I'm going to move to that state. I'm going to use that as the transition that I've got for this. So when the sum is greater than the random, that's our next state. So again, generating random number for the transition from bread, I'm going to choose the denominator here. They're 5. I'm going to generate that random number. And then in the same order, every time I leave these states, I'm just going to keep a running sum of all the outgoing numerators. And I'm going to keep switching between those until I get to a point where the sum that I've got is greater than the random number that I've generated. So to start with bread to peanut butter, I'm going to ask the question, is 3, the sum that I have right now, greater than the random number that I've generated? If it is, then great, I'm going to make that choice. If it's not, I'm going to choose the next edge and add that to my sum and ask that same question. Is this greater than the random number that I generated? If it is, great, I'll move to that next state. If it's not, I'll move to the next edge and do the same running sum exercise over and over again. We'll do the same thing here just really quickly from ham, for example. We've got 2 possible outcomes here. We've got 1/3 and 2/3. If I'm in the ham state, I'm going to generate a random number between 1 and 3, inclusive. Gosh, what's a random number between 1 and 3? 3, okay, good, thank you, yes, okay. We'll say that the random number that we've generated is 3. We're going to start at this outgoing edge from ham. We're going to keep a running sum of the numerators. We're going to add 1, the numerator that we have here, to our running sum. And we're going to ask the question, is that running sum now greater than the random number that we generated? It's not. Move to the next edge. Add the edge weight, so add the 2 here to that. 2 now added to 1 is greater than or equal to our random number. That's true. I'm going to use that outgoing edge. I'm going to move to that state here. We generate 1 as a random number. From the ham state, I'm going to generate a random number. I'm going to say that it's 1. If I generate 1 as a random number, I'm going to start with this outgoing edge. I'm going to add 1 to my running sum. It is greater than or equal to the random number that I've generated. And so I'm going to move to the cheese state. I'm going to use that as my next state here. I generate 2 as my random number. I'm going to add 1 to this sum. 1 is not greater than or equal to 2, so I'll continue on to the next edge and look at that. I'm going to add 2 to that. 3 is greater than or equal to 2, so I will move to that state as the next one I'm going to work with here. So I'm going to generate these random numbers, keep a running sum of these edges that are outgoing as I'm going through this, and use that to help me decide which state to move to. Looking out and seeing a lot of puzzled looks right now. Yes.
So the random number remains fixed as we iterate over the row.
Once we're in the state, once I'm in the ham state, I roll the dice. And then once I've rolled the dice, it's fixed while I'm in this state. Because I'm using that to decide which one to go to next.
With the greater than or equal to now added, that means that we do not have to loop again. It's just one iteration over all the things that we have.
The loop part is going to be this part here. So I generate the random number. That happens once in the state that I'm in right now. And then I'm going to loop over all of the outgoing edges from that state. So with our adjacency matrix, that is, if we are currently in state ham here, I'm going to have to generate a random number between 1 and all of these values would be 3 in the model that we've got. And then for each of them, I'm going to have a running sum as I step through all of these different edge weights. And only when the running sum is greater than the random number that I've generated in the first place, once I hit that threshold, then I'm going to use that index as the next state that I'm going to go to. Yeah.
So this is just a way to help us randomly decide which transition we want to take, as opposed to calculating a number between 1 and 100.
Yes. You're very welcome to implement this as like generate your distribution between 1 and 100. And if you want to use stats to do this with actual proper distributions of the different transitions that you can make, I welcome you to do that. But this is a little bit easier to implement than doing that kind of a thing. Yeah. Any other questions about this right now? Okay. Yeah. We can do the 1, 2, 3 exercise again, yes. So going from ham to our other states. So with the ham, I'm going to erase all of the structure that we've got here. Whoops. To go from ham to the starting state, we never go there. To go from ham to bread, we're going 2 out of 3 times. To go from ham to peanut butter, we never go there. To go from ham to jam, we never go there. To go from ham to ham, we never go there. To go from ham to cheese, we go 1 out of 3 times. With the denominators, what we've got here is 3, 3, 3, 3, 3, 3. And as we discovered last time, we could just collapse this down into one single column for that. With this idea, what we're really trying to do is generate a random number. So I'm going to say that our random number is 1. And then for all of the edges that are outgoing from the ham state, we're going to keep track of this running sum. So to go from ham to the start state, the running sum would be 0 because we never go there. To go from ham now to the bread state, 2 out of 3 times we would go there. My running sum becomes 2. That means that it's greater than the random number that I've got. And so in that case, I would take the ham to bread transition. If my random number is 2, I would do the same thing. I'd start looking at the start state first. We never go there, so my running sum would stay 0. I add 2 to it. Now it's going to be greater than or equal to 2, so I'll take that ham to bread transition. If my random number that I've generated is 3, then what I'm going to say is functionally the same. I'm going to start here looking at the start state. My running sum for this is 0. This is less than or equal to 3, so I'm going to, or less than 3, so I'll keep continuing. I'm going to add 2 to that. My running sum is now 2. That's still less than 3, so I'm going to keep going. I'm going to add 0. It's still less than 3. I'm going to add 0. It's still less than 3. I'll add 0. It's still less than 3. I'll add 1. It's now greater than or equal to 3. And so that means that I'm going to take that cheese state as opposed to the bread state. Does that clarify the idea for you? Okay. Okay. All right. Okay. Okay. Great. The last suggestion I have for you is that you should seed your random number generator. Seeding your random number generator is an idea that really is about making sure that we have predictable outputs from the random number generators that we're getting here. I'm telling you that you should use a pseudo-random number generator, but you are definitely going to be using a pseudo-random number generator. You don't really have much of a choice about this in terms of the number generators that you have available to you. I've hidden a picture in the training data. I've hidden a picture in the training data. There are 2 ways to produce random numbers. Yeah. No. There are two ways to produce random numbers. One is truly random number generators, and truly random number generators are typically hardware-based. And when I say hardware-based here, I mean like dice. Like rolling a dice is a truly random number generation, assuming you don't have weighted dice and assuming you have a flat surface and lots of other assumptions. But like when you're rolling dice, it's a truly random number generation. There's nothing in the background. You just roll it and it goes. This can also be things like background radiation sensors. So like there are USB devices you can plug into a computer that are really just like Geiger counters that are just keeping track of background radiation. There are sensors that you can have that are USB devices you plug into your computer and it will like detect cosmic rays hitting your device. And that will be used as random number generation, a source of random number generation. You don't really have access to those kinds of things other than dice, and dice you can't meaningfully use in software without having cameras and stuff. So the other option is to use pseudo-random number generators. Pseudo-random number generators are algorithms. It's a sequence of steps that you can use to derive a sequence of random-looking data. Very good pseudo-random number generators will generate data that is uniform across all of the points that you have as possible values in your kind of space for random number generation. These are algorithms, and the way that they work in terms of generating sequences of numbers is that they use this concept called a seed. This is the starting point that will be used for the algorithm to generate data. Sequences that are generated by this, and when I say sequences of numbers here, I mean like it generates 1 and then 5 and then 7. This sequence of numbers is deterministic given the seed. So if you provide a seed to a pseudo-random number generator, it will generate the same sequence of numbers every time you start it over again from that same seed point. It's deterministic given the seed that you've got. This is a very bad random number generator, but it's technically a valid random number generator. There's a seed of 4 and it just generates the same number over and over and over again. This is a terrible random number generator. Yes? Sort of. So the question is, does it hash a seed into a number? Sort of. I'm going to show an example of what I mean by this idea. I'm going to show you this link. This is a Wikipedia list of random number generators. There are many different pseudo-random number generators that have been developed really over centuries, but these are kind of spanning the last, couple decades. I want to take a look at a specific kind of number generator that's called the middle square method. And I want to give you this strong caveat that you should never actually use this for anything. I'm just showing you kind of what random number generators do under the hood. I want to give you a sense of what this looks like. Nobody uses this in practice. It's really just to get a sense of what the structure of this looks like. So I'm going to pop over here. The way that the middle squared method works is that we're going to start with a seed. I want to have a number that has n digits in length, where n is an even number. So I would like to start with, I'm going to start with a 4-digit number here. Rather than asking for a 4-digit number, I'll ask you to give me 1 digit at a time. So just shout numbers out, please. That's 2 digits, just 1-digit numbers. 86, okay. Well, okay, that's also 2 digits, but that's fine. Okay, so we have 0386. For the purpose of this, I'm going to invert these. I'm going to say 3086. In terms of the random number generation that we're going to start with, I'm going to call this our seed. This is the seed. The method that we use for this middle square method is we take this n-digit number And our goal is to generate more n-digit numbers. So I want to keep generating more 4-digit numbers as an output from this. So I want to generate a sequence of 4-digit numbers. To do this, we're going to square this number. I cannot do this in my head, and so I'm going to open up my calculator here. And we're going to say 3086 squared is 9523396. So we squared this number and we get this as an output. The next number in our sequence using this middle square method is going to be the middle 4 digits of this number. This is an odd number of digits, so I'm going to prefix a 0 on this. And so the middle 4 digits that we have for this are 5233. Thinking about using random numbers in Java, you've all done like new random.nextint. Yes, yes, I think you've done that. So you've done something like new random.nextint. We're effectively calling nextint, and the next int that we're getting out from this now is 5233. To get the next number in the sequence, we say 5233, and we square that, and we get out from this 27384289. And the next 4-digit number that we get out of this is 3842. To get the next int from this, I'm going to say 3842 squared. And what we get as an output from this is 14760964. The middle 4 digits from this are 7609. And I would keep going with this exercise, but that would be painfully tedious for us to do this. The important part here is that if I restart this number generation sequence and I provide this same seed, doing these operations will always get me the same sequence. If we start with 3086, we're always going to get 5233 as the next number. And then we will always get 3842 as the next number. And then we will always get 7609 as the next number in the sequence of data that we get out of this random number generator. Just use math.random. That's kind of the only choice that you've got with JavaScript. But the problem with this is you can't actually provide a seed to math.random in JavaScript. It's not exposed as a possible option. Unfortunately, JavaScript, I don't know if you've heard this story, but JavaScript was like written in, I think, 10 days, some absurdly short amount of time. And amazingly, they didn't think about stuff like this in the 10 days that they had to implement the first version of JavaScript decades ago. Math.random doesn't let you provide a seed. And so I'm going to strongly recommend that you use this person's math.seedRandom. I provided a link to this here, but I've also provided a link to this on the course webpage. I provided a link to this as well as something that you can use for TypeScript to get types for this. But the idea with this is that I can provide a seed to my random number generator. And I can generate random numbers. And if I keep clicking this, it's always going to generate the same sequence of numbers. Nothing seems to be happening here, but it's because it's generating exactly the same sequence of random numbers. If I change the seed to something else here, it will always generate the same sequence of random numbers. And if I go back to Toro equals Snorlax here, it generates the exact same sequence of numbers as it generated in the first place. In this case, it is literally hashing a string to get a number, but seeds are more commonly numbers. They're actually numbers that you give to something to start with here. But why? Why do we care about this? The main reasons that you care about this are about being able to reproduce sequences of random numbers from the perspective of, I want to make sure that every time I use this random source of information, the same thing happens, at least in certain contexts. One of those might be, I want to make sure that when I'm evaluating my Markov chain, I don't just get different outputs every time. At least for the case of, I want to see that it's working correctly, I want to make sure that I get the same sequence of outputs from this Markov chain. So I want to get the same random numbers every time I choose which state to go to next. More practically, if I'm doing a simulation that uses random numbers, I want to be able to show that, given this random number sequence that I've got, I can reproduce it. I can rerun it over and over and over again and get the same outputs every time I run this experiment. But this also means that you can now start to write tests on code that uses random numbers as a source of information. If you can provide a fixed seed, you can guarantee that every time you run your test, you will get the same sequence of outputs from this random number generator. That's not practical from the perspective of your parents using this code. You do want to actually have random numbers here. But in terms of running tests against something that uses random numbers, you can use seeds to accomplish this task. All right, so at this point, you really should be able to describe and implement basic AI algorithms. So Markov chains, you should be able to build a chain on paper. You should be able to start building a chain in code. You should have ideas about how you can start to do this transition between different states in the Markov chain. I do want to stop here for 1 second with relation to Markov chains. And I want to call to your attention, if you are interested in this, the courses that you should be looking forward to at the 3000 level for Markov chains are Comp 3360. So this is machine learning concepts and usage. This is a relatively new 3000 level machine learning course. And the people in our department that you should know about that are kind of interested in this stuff, there's 2 people that I'll call to your attention. The first one is Dr. Chris Henry. Chris is doing some really cool stuff with AI and machine learning around agriculture related topics. So he's doing a lot of neat stuff around, he gave a presentation to the department last week on Friday. And the stuff that he's doing, gosh, he's got these robots that drive around fields and they've got cameras on them and they basically pick out weeds. So like they can use these cameras to identify weeds. And part of what he's doing with this is using AI and machine learning, not just for the visual identification of the weeds, but to generate massive training data sets, because it's expensive to go and send somebody out to a field and take pictures of weeds. It's really expensive to do that, even when you have controlled environments. And part of what he was talking about on Friday with his research talk was about using Markov chains for this. So to some extent, and like we've done lots of hand waving with Markov chains, he's applying the same kinds of basic ideas that we have for this. The other person I want to call to your attention is Dr. Sadaf Salakalabar. So Sadaf is another person that's doing a lot of AI and machine learning stuff. The last time that I saw her give a talk, she was thinking about things like pose estimation, and then also about doing things related to like video compression using AI and machine learning topics. So those are a couple of people that you should know about in our department that are related to that. On top of this now, you should be able to distinguish between pseudo-random and truly random number generators. Truly random being literal hardware-based things. Pseudo-random, this is an algorithm that you can use to generate sequences of data. And you should be able to use pseudo-random number generators for reproducibility. You should be able to at least have a sense of, I need to provide a seed to this thing so I get the same outputs every time I run this. That's it for today. Thank you all for sticking around, and I'll see you on Thursday. Bye, everybody.